The quotient rule says if you have a function f of x equals a numerator over a denominator, in other words, the function is a quotient, the derivative of the function can be found by taking the derivative of the numerator multiplied by the denominator minus the numerator multiplied by the derivative of the denominator over the denominator squared. And I mentioned yesterday in class, just formally announce it here, that your unit exam is a week from this coming Tuesday. That'll give us a couple of days to practice differentiation before we finish the unit, and then after we finish the unit, it'll give us a couple of days to review everything. Does anybody have any questions you would like me to go over? Yes, Isaac.
6.
Number 6. Great question. It's a very important question for a number of reasons, and they're going to become apparent as I go through it. At what points on the curve given is the tangent line horizontal? The first thing that I want to draw your attention to, and it's not the first time I've done so, is that a tangent line that is horizontal has a couple of features to it. One, it has a slope equal to 0. What that means is the value of the derivative at that particular value of x is equal to 0. And I'm putting that kind of a subscript there because I don't want to say dy dx equals 0. Yes, dy dx equals 0 there, but I don't want to leave you with the impression that the derivative is 0. The derivative at a particular place is 0. But what's more important is, and there's going to be some twists and turns to what I'm about to tell you, that it's more complicated than what I'm about to tell you. But I'll stick with y. These points where the tangent line is horizontal, for the most part, correspond to maxima or minima. That's the words we use for plural of maximum and plural of minimum. So if I have a graph that looks like this, then I know for a fact that at this point, and this point, the slope of the tangent will be 0. And I think we can kind of decipher that just by looking at it. That the slope goes, if we focus on this first point here, the slope goes from being positive to the left to negative on the right, which means that the tangent line will be horizontal. And this is a way that we are able to determine where things are as big as possible or as small as possible. How economists can maximize the revenue is they look at a revenue function and they determine where the derivative is 0. And at that point, whatever those sales are, that corresponds to the maximum revenue, or perhaps minimum revenue, who knows. So what we need to do here for this question is find the derivative and set it equal to 0. If y equals x squared over 2x plus 5, thank you, over 2x plus 5, I don't want to say it's a trivial matter to find the derivative, but as every day clicks by, some of this stuff becomes more and more natural. It has to. The derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom squared. And again, there's that, well, you can't see it because you can't see what's going on in my head. I'm on autopilot when I'm doing that, so I'm not even really thinking. At least it doesn't seem like I am. So I'm going to double check that. Derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom squared. I think that's fine. Now you have to follow these aren't rules. There are ways to do the rest of this problem without following my steps. But I always recommend you factor before you multiply. Specifically, what we're looking at here, Isaac, is in the numerator of this expression. We have this term minus this term, and they both have factors. 2 is a factor of the first term, x is a factor of the first term, 2x plus 5 is a factor of the first term, x squared is a factor of the second, and 2 is a factor of the second. And I hope it's obvious that when I say x squared is a factor of the second, that means x is a factor of the second. I have a 2 as a factor in each and x as a factor in each, so I can factor that out. And this factoring before simplification is not just because, I'm that type of person. It needs to be done that way. It's helpful, and you're going to see why it's helpful in a minute. What do I have left? Well, I factored the 2x out of the first term, so I have 2x plus 5 left. And out of the x times the 2 in the second term, I factored out the 2 and the x, so it leaves me with one more x. And now I can clean this up, and I'm going to answer the question. I have 2x as a factor and x plus 5 as a factor, because I have 2x minus x in brackets, over 2x plus 5 quantity squared. And I want to point something out to you. When you have a fraction, if that fraction is equal to 0, it's where the top is equal to 0. If I have a fraction and I want to find out, and I don't in this question, but I will later, I want to find out where this is undefined, then that's going to be where the bottom is 0. Because, look at this, because this is written as entirely factored on the top and the bottom, I can look at this and tell you that this is equal to 0 when x is 0 and when x is negative 5. I mean, I'm not even really solving an equation. I'm not doing anything algebraically. I'm just saying what value of x makes that factor 0? 0. What value of x makes this factor 0? Negative 5. And I don't know, this morning, when we did this morning, did we find the y coordinates? We did. I'm not going to. It says where is the slope 0, or where is it horizontal? Well, it's going to be horizontal at 2 different points. And if you want to find the vertical location of those points, which includes the y coordinate, you have to put each of those x coordinates back into the original function. And this morning, when we had a little bit more time, we graphed the function and looked at, oh, there it is. There's a maximum and there's a minimum. I think it was a max and a min where the tangents were 0. We could even draw them, but I don't think we drew the tangent lines. No, we didn't. Anyway, does that do it for you? Okay. By the way, and if I wanted to know, and you don't know why this would be the case, if we want to know where the derivative is not defined, we just look at this and say negative 5 over 2. Always factored over factored. It has applications. Other questions? All right, we're going to move on and look at the most, I think it's the most important rule in differential calculus, which is called the chain rule. And the reason why it's the most important rule is it's not a rule. Well, when you have the product rule, you use the product rule when you're dealing with a product. When you have the quotient rule, you have a rule that you use if you're dealing with a quotient. The power rule is used when you're dealing with a power. The chain rule is used all the time. In fact, we have been kind of using it already, although we didn't notice it because it wasn't necessary. So you use the chain rule for products, and you use the chain rule for quotients, and you use the chain rule for trig. And for exponential functions, and for all those functions and powers. Everything involves the chain rule. So we're going to be learning about the chain rule today, and then correctly interpreting derivatives, which simply means finding slopes of tangents using derivatives. I will let you know that functionally speaking, you can get through calculus, even post-secondary calculus, without understanding the chain rule at a deep level. You learn how to use it, and you have no idea how it works. It's like your phone. I don't think too many of us really understand what's going on in that piece of magic, but we know how to use it, okay? The big difference between your phone and calculus is actually useful for things. All right, phones are useful. But when I see students doing this all day long, I don't know how useful that is. All right, off my soapbox. So I'm going to attempt to teach you the deeper understanding of the chain rule, and some of you will get it. I don't mean to imply that it's so difficult you're not capable of doing it. But if you get frustrated and you just can't wrap your head around it because of the complexity of it, that's okay as long as you know how to apply it. Okay? So we're going to warm up with three functions. I have y equals f of u, and what that means is y is a function of u, this first function on the left. Y is a function of u, and what that means is, you people who have finished Math 30 have an advantage over those who haven't, is that you put u in and y comes out. Okay? What it means is that you can calculate y knowing the value of u. It's like u is our x. And then we have another function, u equals g of x, and that means that x goes in and u comes out. If I say that u is a function of x, and I'm just using the letter g here because I don't want to repeat the same letter. If I say u is a function of x, that simply means u can be calculated if I know x. And some of you are going to start to see, if you finish 30-1, we're talking about a composite function here. Okay? And those of you that are in it right now don't worry about that. And then I also have y equals f of g of x. What does that mean? It means I have a function in which g of x goes in and y comes out. But with a little bit of thought, you will see that the first function and the third function are the same. Because u and g of x are the same. U equals g of x. So whether I talk about what I wrote in red on the left, which is saying u goes in and y comes out, or I talk about what's written on the very right by saying g of x goes in and y comes out, it's the same thing. It's just that I'm saying u is going in one and g of x is going in the other, but they are the same. So this is y in terms of u, this is u in terms of x, and this is y in terms of x. And again, these two are the same, really. They're the exact same function, just looked at slightly differently. So what are we going to do with this? We're going to find dy du, and this is the first time we've been asked to find a derivative with respect to something that's not x. Okay? But and please don't write what I'm about to write down, because I don't want to mislead you. If I told you instead of y equals u cubed, if I said y equals x cubed, and the reason I don't want you to write it down is that's just not the case. Okay? And I said, what is dy dx? Well, it's 3x squared. The dx on the bottom is simply saying that's the variable whose rules are in orbit around. That's the variable that you look at applying the rules to. So when I say the following, when I say y equals u cubed, and I say what is dy du, it's 3u squared. It's not complicated, it's just using a different letter. And there's, for many of us, we're going to go through a lot of this warm-up and you're going to be wondering what the point is. And then the light will start to come on if you're fortunate enough to understand the deeper meaning of the chain rule. And if it doesn't, just hang in there. What is du dx? Well, u is equal to 2x minus 5. So if I differentiate u with respect to x, I just differentiate 2x minus 5 with respect to x, and I get 2. Are you with me on that? All right. Now, what is dy dx? Well, now we have to look at a function. Let me go back here. When we wanted dy du, we looked at the function that contained a y and a u. When we want to find du dx, we look at the function that has u equals in terms of x. If I want dy dx, I need a function for y in terms of x. And y is f of g of x. But g of x is 2x minus 5. So y is f of 2x minus 5. But f of u is u cubed. So f of 2x minus 5 is going to be 2x minus 5 cubed. And we have to figure that out, because to differentiate this with respect to x requires the use of the chain rule, and you don't know it yet. Okay? So this involves taking 2x minus 5 multiplied by 2x minus 5 multiplied by 2x minus 5. And I'll be honest with you, I think using the binomial theorem here for just a product of 3 binomials is not necessary. If you're familiar with the binomial theorem and you want to go that route, you can. This will be equal to 4x squared minus 20x plus 25, I think. Times 2x minus 5. So now everybody in the first factor, everybody in this factor has to dance once with everybody here. So I am going to start with the 4x squared. 4x squared times 2x is 8x cubed. 4x squared times negative 5 is negative 20x squared. I'm done with the 4x squared, but I should probably just check those two products first, and I believe they're fine. Now I move on to the negative 20x. Negative 20x times 2x is negative 40x squared. Negative 20x times negative 5 is positive 100x. I'm going to double check that, and I ask all of you to double check my math as well, but I'm sure that's fine. I'm done with the negative 20x. And by the way, I said, oh, I'm sure that's fine, and I never really checked. Be careful not to derail yourself that way by just saying, oh, I'm really confident it must be right. But it is. Okay. Now I go to the 25. 25 times 2x is 50x. And 25 times negative 5 is negative 125. So we can add those together. And I already have it added together on the next page, so I'm not going to write it. But you get 8x cubed minus 60x squared. You get plus 150x minus 125. Okay? So that's what we get. And now we can differentiate it with the sum and difference rules and the power rule. I take 8x cubed and I differentiate it and get 24x squared. Negative 60x squared has a derivative of negative 120x, and 150x has a derivative of 150. And again, I find it easier to differentiate if I'm not talking at the same time. So I just have to look at it now, and we're good. On the heels of what we just talked about with the example that Isaac asked about from yesterday, we want things in factored form. And I see that I'm pretty sure these are all divisible by 3. Is there a bigger number than 3? I don't think so. So I can factor a 3 out. And what else can I do? Well, I have 8x squared minus 40x plus 50. Is that factorable? Now, some of you, I'm not one of these people. Some of you go, yeah, it's factorable because you can see, like Neo in the Matrix, you can see immediately that it's factorable. I got to do the b squared minus 4ac thing. That's the only way I can do it with something like this. Although I do happen to know a little bit more about this question. But b squared minus 4ac would be 1600. That's negative 40 squared minus 4 times 8 times 50. And that's 0. 0 is a perfect square. Yep.
Can we factor 2 out of it?
Oh, so there was a bigger number. That's what I wanted to know before. There is a bigger number? Oh, yeah, because those are all even now. 6. We could have factored a 6 out. Let's go back and do that. Or, Annalie, you could certainly just factor the 2 out now and combine it with the 3. You don't have to erase it if you don't want to. Well, that'll make our factoring of the quadratic a lot simpler, won't it? In fact, I was wondering why we weren't getting a quadratic that I thought we were going to get. You'll see what I mean in a second. So I factor a 6 out. That's 4x squared minus 20x plus 25. Wait a minute. That looks awfully familiar. 4x squared minus 20x plus 25 is 2x minus 5 quantity squared. And again, the lights are going to start to come on sporadically here in terms of what's going on in terms of the derivatives. That means dy dx equals 6 multiplied by 2x minus 5 quantity squared. All right. So now, so what? What do we notice about the relationship between the three derivatives? Well, let me write out what dy du is. And I'm going by memory here, but I'm pretty sure dy du was 3u squared. And I'm going to write down what du dx was. And du dx was 2. And I'm going to write down what dy dx was. And it is 6 times 2x minus 5 squared. Does anybody see the relationship between those three derivatives? Go for it.
So the 3u squared and the 2, when you multiply the 3 and the 2 together, you get 6, and because u is 2x minus 5, you put that in for the u, and it's squared.
Jackpot. What we've discovered, and granted, this is just one illustration, but this is true always in this scenario, is the following. That if you multiply dy du by du dx, you get dy dx. Okay? This derivative multiplied by this derivative gives you this derivative. Now, as Isaac pointed out, there's a little bit of substitution required to see that. Since u is 2x minus 5, we could put 2x minus 5 in over here for u to show that when you multiply dy du and du dx, you get dy dx. Now, if you're like me, and maybe 99% of calculus students, the first time you see this, you go, well, of course that's true because of that. But you can't cancel that. And this is where things get pretty slippery on the brain. The reason you can't cancel those is dy du is an instantaneous rate of change of y with respect to u, which means du is infinitely small. Whereas du dx is a rate of change of u with respect to x, which means x is getting infinitely small. Your du in one is not the same as your du in the other. Derivatives are not to be treated as a fraction. So, what does this mean? It means that if you want to find and I have to really choose my words carefully because it's tricky. If I want to find the derivative of something with respect to x, I can find the derivative of it with respect to another variable that depends on x, and then I can multiply by the derivative of that other variable with respect to x. So there is a shorter way to determine dy dx in this question, and it uses what's called the chain rule. And I'm going to come back to the details of it in a bit. But in the meantime, I want to give you an explanation in a different analogy, using a different analogy, as to why this should make sense to you without resorting to canceling anything. Forget about this warm-up, look at that only. If dy du is a rate of change of y with respect to u, it's telling you how rapidly y is changing compared to u. And du dx would then be telling you how rapidly u is changing compared to x. I don't know to how many of you it makes sense then that dy dx would be the product of these, but I'm going to give you an analogy here, a couple of them. If y is changing 3 times as fast as u, and u is changing 4 times as fast as x, parse that in your head and see if it makes sense that y must be changing 12 times as fast as x. And if it doesn't, another analogy, and I admit I was having a difficult time when I first made up this analogy coming up with names, so you just have to live with the names because I've never changed them. If dy du is 3, and y represents Yvonne, and u represents Umberto, I couldn't come up with a person's name that started with U. Then what that means in terms of an analogy is Yvonne is running 3 times as fast as Umberto. If du dx is 4, and u is Umberto, and x is Xavier, then that means that Umberto is running 4 times faster than Xavier. So, you know, on the one hand, Yvonne is the fastest when you look at this first statement. And over here, Umberto is faster than Xavier, but Yvonne is faster even than Umberto. It makes sense, doesn't it, that Yvonne is going to win the race by a factor of 12? That's one way you can kind of wrap your head around it. I still haven't given you the functional definition. Like, how do you just, forget about explaining it this way. What do I do? We'll get to that. Okay? This is the chain rule that we've just written. Dy dx equals dy du times du dx. This is the chain rule using, I want to say Leibniz's notation. I could be wrong on that. The derivative with respect to x of a function of g of x, not of a function of x. This thing here depends on x. This thing is not x, it's something else that depends on x. Is found by differentiating the function with respect to that thing that depends on x, and then multiplying by the derivative with respect to x of that thing that depends on x. And what we did in our example, everybody, and what's traditionally done, is that. We're calling the thing that depends on x u. And when we learn the chain rule for trig and for exponential and for other situations, I'm going to come back to this, and more students typically will start to see the deeper meaning. That if you're going to differentiate a function of x with respect to x, you have to differentiate with respect to that function and then differentiate that function with respect to x. Okay. And I'm going to be mentioning this many times. This is basically saying what's the derivative of the argument. Don't worry about writing that down, but I just wanted you to see that word. So, use the chain rule to find the derivative of this without messing around with all that other stuff. So, would you agree that the big picture is y is a power? Y is a base raised to an exponent. Yeah? That's the big picture. Forget about what the base is. Y, first and foremost, is a base to an exponent, which is what we call a power, which means you use the power rule. But when we do this, and we write 3 times 2x minus 5 squared, we have not found the derivative with respect to x. We've found the derivative of y with respect to 2x minus 5. Because 2x minus 5 is the argument of the power. We still have to multiply by the derivative of the argument, which is 2x minus 5. Your textbook and most instructors I've seen would have you start using the chain rule by doing this. By saying we are going to let u equal 2x minus 5. That means the function becomes y equals u cubed. Then they will say the chain rule says I want to find dy dx, which is dy du times du dx. So they'll differentiate this to get dy du, which is what I have over there. Times they'll differentiate this to get 2, and then they will resubstitute in the 2x minus 5. The chain rule that basically just says differentiate with respect to this. So just wrap your exponent around it, do the rule, but then multiply by the derivative of that. So you get 6 times 2x minus 5 quantity squared. That's the derivative. If you knew the chain rule, you could have done assignment 1b without using limits, or without expanding it out like you did, Reagan. So now to get to the functionality of it, the operational definition. What do you need to know to find a derivative? Well, in terms of a power, which is really the basic rule that we're talking about here today, for now, if you want to differentiate a number times a function of x raised to a number, you wrap the exponent around to get a new coefficient. You drop 1 from the exponent. The base remains the same. No matter how big or complicated it is, it stays the same. Then you multiply by the derivative of what's inside. And that's often what you'll see in textbooks. Multiply by the derivative of what's inside. And as well, this is probably the better way to look at it. The derivative, well, I want to show something to you. Is this familiar to you? That's the power rule, right? This works as long as the base is x. If the base is something that's not x, then you still apply that same rule, then you just multiply by the derivative of that base. This is the functional way to look at it. Without understanding why it works, that's what you do. So let's take a look at some examples, remembering that we have to follow the rules. So, what is the derivative of y here? I hope everybody would agree nobody wants to foil's the wrong word, nobody wants to take that trinomial and multiply it by itself 3 times. Especially when you know that the derivative has to be put into factored form. So if you multiply this out, you're going to get a degree 6 polynomial, which if you differentiate will turn into a degree 5 polynomial. Now you're doing the stuff that we were doing this morning in Math 30-1 and that you guys were doing on your diploma exam, which is even more than the diploma exam because this would be a degree 5. So what do? We say that this is a power of that thing, so we differentiate with respect to that thing. We pretend that thing is like x, and then we do that, we write that down, and then we wake up to reality and go, no, wait, it's not x. The chain rule says I now need to multiply by the derivative of what's inside of the function of x. And that's going to be 6x minus 4. Yeah? Okay. Can we factor anything? Well, there's a common factor of 2 in the 6x minus 4. So I can factor that out and marry that 2 that I factor out with the 3 that's in front and just write 6. 3x squared minus 4x plus 1 squared, and then we took a 2 out of this, which means it's 3x minus 2. And that's the derivative. I don't believe that that quadratic is factorable. It is. Let's not factor it, though. It is factorable. B squared minus 4ac is, I believe, 4. Let's not. Be 3x minus 1, x minus 1, I guess. There's not many options there. That's not the point of the lesson. So let's not worry about it. Like this is something you wouldn't have a hope of differentiating. If you used the quotient rule, you would have to find the derivative of the bottom, and the bottom is this. Now, I'm going to recommend something here only because the top of this is a constant. We can avoid the quotient rule in this case because this is 4 over 16 minus x squared to the half. Why don't we just do this? I haven't differentiated anything here. I'm saying instead of dividing by a power of a half, let's multiply by a power of negative a half. That's your negative exponent law, which says that a thing raised to a negative exponent is equal to the reciprocal of that thing raised to a positive exponent, and vice versa. And now, this thing, and I will often use this analogy, and maybe it doesn't make sense to you, it just makes sense to me. If that function that we have here is really far away distance-wise, as you get closer and closer and closer, the first thing you bump into, the outer function, is a power. First and foremost, this is a power. It's a power of a difference, of a constant, and a power. But first and foremost, it's a power. So we use the power rule. I wrap that negative a half around. I multiply negative a half by 4 and get negative 2. The base remains the same. There's a tendency for some students to want to differentiate the base when they do this. The base remains the same. I drop 1 from the exponent, and then I multiply by the derivative of what's inside. Of course, we don't like negative exponents first thing is negative 2 times negative 2x. I mean, yeah, we want things factored, but you don't write negative 2 times negative 2x. You write 4x. Over 16 minus x squared to the 3/2. So we kind of cheated the system here by taking that exponent and putting it up top where it's positive or where it's negative to avoid the quotient rule. And then we don't want negative exponents. We'll put it back on the bottom. By the way, just by inspection, the values of x that make this derivative 0 is 0. And there are two values of x that make the derivative undefined, positive and negative 4. Because the bottom can be factored into 4 plus x, 4 minus x. Although I think many of you would just look at this and go 4 and negative 4. Okay, let's try another one. Whew. I want to know if this is written up here the way it is in your notes, other than the fact that it's square brackets. So this is a power, and we're going to do this two ways, okay? And you have enough room to do it two ways. And you're going to have to come to a decision as to which way you like. And what you're going to discover, by the way, is sometimes you'll try it one way and finish it and then realize that if you did it a different way, it's easier. Sometimes you'll try it one way and go, oh, yeah, that was easy. Okay, it depends on the situation. This is a power. It is a base that is raised to an exponent of 6. So we wrap that 6 around this base, which stays the same, and we drop 1 from the exponent. By the way, I use square brackets up here because my round brackets in this program look like garbage when they're big. Okay, that's all. But that is not the derivative. I now need to multiply by, what I'm going to put in here is going to be the derivative with respect to x of that base, which is 4x minus 3 over x plus 2. I have to multiply by the derivative of what's inside, of the argument of the power. And if it was not a power, maybe it was sine of that thing, then I'd have to multiply by the derivative of that argument. It doesn't matter what the operation is. Of course, you don't know what the derivative of sine is, but it's a different story. So that's a quotient. I'm multiplying right now by the derivative of this thing, which is a quotient. So I follow the rules and I take the derivative of a quotient, which is the derivative of the first, or the top, times the bottom, minus the top, multiplied by the derivative of the bottom over the bottom squared. And there's a multiplication in here, right? You know, even if this term and this term had a common factor, how many of you see, since everything's linear, it's just as easy to multiply it out anyway? And if you get a common factor, deal with it. But there is no common factor, so I'm just going to multiply that out. What do we have? dy dx equals 6, and then we have 4x, well, we have 4x minus 3 to the 5 over x plus 2 to the 5. I think many of you will understand why I've chosen to look at it that way, because I have an x plus 2 squared over here that's on the bottom. So I'll be able to bring these two together and write x plus 2 to the 7. You should have discovered this yesterday. Well, we talked about it in the lesson, but in your practice you should have discovered, remember I said that the x's in the quotient rule very often just slip away? Well, that's what happens here. You have this 4x minus another 4x is nothing. Then we have 8 plus 3. By my count, that's 11. Just checking. It's late in the day. 8 plus 3. Yep, 11. Bringing this all together, rather than, we're multiplying two fractions here, rather than multiplying one times another, this is like one fraction. We can multiply across the top and get 66, 4x minus 3 raised to the 5 over x plus 2 raised to the 7. Are we okay with that? Yeah, there's another route you can take. Part of my brain says I would rather do this, but I don't know. Let's do it and find out. I might change my mind. See, what I can do is, since the entire thing is raised to the 6, I can apply that power to the numerator and denominator. The difference here is this. This is a power. Just wait for that to go away. That's a power. What is it a power of? It's a power of a quotient, but it's a power. This is a quotient. First and foremost, it's a quotient. It's a quotient of two things. It happens to be a quotient of two powers, but it is a quotient, which means instead of using the power rule, which I started off with here because it was a power, I'm going to start off with the quotient rule. All right. The derivative of the top is 6 times 4x minus 3 raised to the 5. Are we in agreement that that's the derivative of the top? Man, I just suckered too many of you in. It is not the derivative of the top. What am I missing, Jack?
You need to take the derivative of the argument and multiply.
Right. I need to multiply by the derivative of the argument of the function, which is the base of the power, which is 4x minus 3. In other words, if you want to just be specific to what we're dealing with so far, you need to multiply by the derivative of what's inside. That's the derivative of the top, times the bottom, which is x plus 2 to the 6, minus the top, which is 4x minus 3 to the 6, times the derivative of the bottom. Would you agree, or is it true, that that's the derivative of the bottom? 6 times x plus 2 to the 5. Well, I'm glad you're shaking your heads. It turns out it is, because I need to multiply by the derivative of what's inside, and the derivative of x plus 2 is 1. And in every case, you can go back and check this out, in every case where you differentiated with the power rule before today, the derivative of what was inside was 1, which is why you didn't need to worry about the chain rule, because the base was always just x. Now I have to go over the bottom squared. If I square a power of 6, I'm going to get a power of 12. You can certainly write raised to the 6 raised to the 2. And now, well, the steps that you need to follow to be successful is that when you look at the top, there's two terms: factor out what you can and simplify the leftovers. So there's a 6 as a factor in both, isn't there? I can take a 6 out. I've got boatloads of 4x minus 3s. Well, not boatloads. I have 4x minus 3 to the 5 in one term and 4x minus 3 to the 6. So we take out the lowest exponent. We learned that on day 1. I also have x plus 2's running rampant. I have 6x plus 2's in the first. I want to be careful here. When I say 6x plus 2's, I don't mean 6 times x plus 2. I mean x plus 2, x plus 2, x plus 2. I mean I have 6 factors of x plus 2. And I have 5 in the second, which means I can take out 5. What do I have left? Well, I have a 4 and an x plus 2 minus, I have a 4x minus 3. Some of you should start to see that this is turning into what we had last time. That what I have in brackets is going to turn into 11, I think. And I'm going to end up with x plus 2 to the 7 in the denominator because I've got 12 factors of x plus 2 there now, and I have 5 in the numerator. So this thing in brackets, I'm not sure why I drew it so big. This thing in brackets on the top that I'm underlining in green, what do we get? 4x minus 4x is a wash. 8 minus negative 3 is 8 plus 3, which is 11. Let's multiply that 11 by the 6 to get 66. We have 4x minus 3 raised to the 5. And, this part in here is like having a to the 5 over a to the 12. It simplifies to 1 over a to the 7. So we can put x plus 2 to the 7 there. And again, it is late in the day. My brain is a little foggy. But I think that's what we got before, isn't it? Okay. Once again, especially in terms of the math, there's nothing that I've been talking about earlier in the course, even though it's only been a couple of weeks, that we don't continually go back to. Well, this is a product. This is the last example, I think. Yes? It's a product. So dy dx is the derivative of the first times the second. So what's missing here?
The derivatives of the arguments.
The derivative of the argument of the first. I haven't done the rest of it yet. So I still need to, when I wrap this 5 around this base, which is the argument, and I get 5 times the base or argument stays the same, and I drop one from the exponent, Jack's saying I need to multiply by the derivative with respect to x of the argument. Have a good weekend. We'll see you on Monday. And then times the second. This is the product rule, so now we go plus the first. This one's a little bit easier than the previous one. I'm kind of winding down things for you a bit here. Times the derivative of the second, which is 3, times the argument stays the same. Am I going to make it? Raised to the 2. Just enough room to squeak in that multiplied by the derivative of what's inside. You almost can't afford to be on autopilot anymore. There's so much going on. I'm just running through everything in my head. Second, the first times the derivative of the second, I think it's fine. So now again, we focus our attention on the fact. I better just double check here, as I say, 34 eyes are better than 2. That looks okay though, I think. Okay. What's the common factor? I can't take a 5 out. I can take a 3 out. There's a 3 in both. I definitely have, and I think you can kind of intuitively understand this. When you use the product rule or the quotient rule and you have powers of the top and bottom or powers of the first and second, you're going to be able to factor out some of those powers. I have 3x minus 2 in both. I'm going to factor out to the 4 because they both contain at least 4. I have 2x minus 5s, and one of them has 3 and one has 2. So I'm going to factor out the lower exponent. I don't know that I've ever really said it this way. You're factoring out the lowest exponent because that factors out as much that you can. What do we have? We're left over with a 5 here. We've taken out all of these. We've taken out the 3. We've taken out 2 of these, so we're left with that 3. Nope, I made a mistake there. We took the 3 out, we're left with a 5. Times we have a 2x minus 5. Out of the second one, we took out a 3, so we're left with this lonely 2 over here. We took out all the 2x minus 5s. We took out all of the 3x minus 2s except for 1. And, you know, essentially, if you can simplify what's in that large set of brackets, you're basically done, unless what's in the large set of brackets simplifies to something that turns out to be factorable, and in which case you just factor it. What do we get here? dy dx equals 3 times 3x minus 2 raised to the 4 times 2x minus 5 raised to the 2 times brackets. I didn't double check this line. I better just double check it. No, it's okay. What do we have? 10x plus 6x is 16x. And then I have negative 25 and negative 4 is negative 29. Well, that's not factorable. So that's it. Now, for whatever reason, I don't know who makes the rules. There's a convention or kind of a set of rules that we tend to follow. This rule or convention is something that you can easily break. I don't care about it. Usually, if you see answers typed out, they're written in increasing degree on the variable. So since 3 is a constant number, it's degree 0, there's no x's. This is raised to the 1, this is raised to the 2, this is raised to the 4. I don't care which way you write it. You know, I just want to point out, if you look at the back, the factors may be in different orders. So that's really kind of it for the bulk of the unit now in terms of differentiating. There's still 2 more things we want to talk about with derivatives next week. But the problem set that is attached to this in terms of your textbook, page 103, number 1, number 6, these all involve the chain rule and or the product and quotient rules and power rules. We're going to continue to work with the chain rule and differentiating with all of these rules on Monday for the first half. What it boils down to is probably when you come in Monday and I say, does anybody have any questions? You're probably going to have questions. And that first half hour, 40 minutes might just be me going over questions and us practicing together. But the second half is going to be find the derivative. So if I were to look at, I'll come back to this in a second. If I were to look at this and I were to make a quiz from these questions, I would probably choose something like this, this, and that. That's what I'm kind of talking about for a quiz here. It's not going to be like 8 derivatives that you have to find. You understand now that would take a long time. I do want you to make a note, and I will leave this. I won't leave it up here. Some of these questions, like this one, or this one, or this one, or this one, are just an exercise in you figuring out how to apply the chain rule. You're going to get such an ugly result, you're not going to try to simplify it. Okay? So get to work on those, please.